Hi, everybody. My name is Mel Hanna. I am a senior data scientist at Stable Auto, and I am also a member of the Climate Change AI core team. Today, we're going to be talking through the tutorial on forecasting the El Nino/Southern Oscillation using machine learning. This tutorial does not assume that you have really any data science knowledge, so there's no prerequisites, though it is definitely helpful if you are familiar with Python and maybe know some of the math behind machine learning algorithms. But we are going to walk through things at a pretty introductory level. I'm also not going to be executing any code live here today. Excuse me, please feel free to pull up the notebook and follow along with me as I talk through each of the cells. So first, some background on the use case that we're trying to solve here. El Nino/Southern Oscillation, also abbreviated as ENSO, or as I will say here today, ENSO. This is going to be a mode of variability in our climate that is a seasonal timescale. So it's a really great use case for us to try out some time series forecasting techniques and see how they work in this climate application. We are going to be measuring this phenomenon using the Nino 3.4 index. This is a rolling 3-month average of temperatures around the Pacific equator. And ENSO is an oscillation. So there's two main phases. You may already be familiar with these. El Nino is the first. This is marked by anomalously warm temperatures in the Pacific. And La Nina, conversely, has anomalously cold temperatures. So El Nino is tied to a lot of major weather events, such as the Indian monsoon, hurricanes in the Atlantic, and the temperature in North America. So it's really important that we have an accurate forecast of this particular index, especially for such applications as agriculture, water, and energy. So existing El Nino forecasts currently use dynamical models. And these sorts of models are relying on modeling the physics of the atmosphere and the ocean. We're going to take a slightly different approach here today. We're going to be using machine learning to forecast El Nino and using statistical optimization to do so. So let's go ahead and dive in, run some code. The software requirements will be taken care of for you if you are running in Colab, which we highly recommend, especially so you will have access to a GPU. A GPU is going to greatly speed up the execution time of this notebook, especially later on when we train a neural network. But we are here just importing some pretty standard machine learning libraries, things like scikit-learn, SciPy, PyTorch, etc. There's some links out here to the data sets if you want to learn more about the data that we're using here today. But our input variables are going to be sea surface temperatures, and these are going to be taken at a sampling of latitudes and longitudes around the globe. And our output variable here is Nino 3.4 index. As we discussed previously, this indicates the state of ENSO. So here we have just some definitions of our training, validation, and test set. We're going to be talking a lot more about these concepts later on, but it is defined up here. You can use this as a reference. Specifically, the training set will be from 1980 to 1995, validation set 9706, test set 07 to 2017. But again, more on that later. First, let's back up and just talk about machine learning fundamentals. So there are some resources linked here from UC Berkeley machine learning class. Again, if you are new to these concepts, highly recommend you check these out. They're going to walk through these concepts in a lot more detail, especially exploring the math. But today we're going to be talking more about the intuition. Let's go ahead and install a final package needed here today, and then finally download our data. Now we're going to write some code to do some pre-processing. So this first function here, this is just reading in that data. But let's talk more about this assemble basic predictors predictands function. So first, some definitions. Predictors are going to be those input variables, in this case, those sea surface temperatures. These are going to help us determine and predict the predicand, which is going to be that Nino 3.4 index. This is the target variable, what we actually want to determine. So this function is going to take in several input variables. Let's walk through a few of these. The first is start date. This is going to be the beginning date from which we want to start extracting sea surface temperatures. That's what SST stands for here in this context. And then the end date. The lead time is going to be the number of months between the sea surface temperatures and the target Nino 3.4 index. So if we have sea surface temperatures, let's say from 1990, we have a lead time of 1 year. We're going to then have the Nino 3.4 index from 1991. Though it's important to note that in this case, lead time is a month value, not years. Then we also have some input variables here around PCA. PCA stands for Principal Components Analysis. I'm not going to go into detail about what this technique is. If you're interested, the resources linked here will go into much more depth. But at a very high level, Principal Components Analysis is going to reduce the dimensionality of our data set. And this is especially useful when we're doing types of visualization. One final note here on this particular function regarding lines 50 through 56. So we have a 3D array. So we've got the time steps and then the latitude and longitude of each sea surface temperature. But we are going to be working, at least initially, with linear regression for pretty traditional machine learning models. And so, as noted here in this comment, we're not taking advantage of the spatial nature of this data set. So we're going to need to reshape this, flatten it, so to speak, into a two-dimensional array. So it's going to be time steps versus the latitude, longitude data points that have been moved out into that second dimension. You'll see this again when we talk about the neural network, but I want to call it out up front here when we go through the linear regression portion. And then we also have a function here just to plot the time series. Okay, so let's go ahead and use this function and create our training, validation, and test sets. So earlier we had defined those as certain points in time. Our training set was going to be from 1980 to 1995. We're going to use a lead time of 1 month, validation set 9706, and test set from 07 to 2017. All right, let's go ahead and actually train a machine learning model now. We're going to use linear regression, keep things super simple. And we're using scikit-learn, calling the linear regression model, and we're fitting it on our training set. Then we're going to predict using our validation set, and then run some performance metrics such as Pearson correlation and root mean squared error, or RMSE. And let's plot and see how well our model performs. So in blue here, we have the ground truth data, and in orange, we have the predictions from our model. Our correlation is 0.86, and RMSE here is 0.28. So, overall, not the best model, and you could definitely see that just at a quick glance by looking at this plot. We don't have a ton of overlap between the two lines. Now let's talk a little bit more about the training, validation, test set, how we define those, why it's so important that we're thoughtful about how we define them, and then some pitfalls to watch out for in machine learning models, such as overfitting. So I'm going to skip down to these diagrams here because I think these visualizations are the best way to describe underfitting versus overfitting. So there is a question here. I'm just going to go ahead and answer that for you. We're going to talk about the diagram here on the left. This one is illustrating an underfit model. Underfit model means that the model here is represented by this blue line, and then our data points are here in blue as well, and the true function that the data points are supposed to represent is here in orange. So this blue line, this is our model. It's not doing a great job. You can see that it does not represent this data very well. That's what we mean by underfit. The converse side of this is that we have an overfit model, and that's what we have here over on the right. So we can see our model here in blue. It's attempting to fit through every data point. It's really, overfitting to the data, so to speak, whereas the middle diagram, this is what we're aiming for, where we've got some nice overlap between the model and the true function represented. Now, how does this relate to the training, validation, and test set definitions? Let's go ahead and run some code and figure that out. So for this particular example, we're going to try to predict El Nino for 36 months out into the future. So we're going to set our lead time to 36 months, 3 years out. That seems like a pretty tough task, but let's go ahead and give it a try. We're going to assemble our predictors and predictands of 1990 to 1995. And then we're going to train a linear regression model on X and Y, and we're going to predict on X and take a look and see how well those predictions perform. And incredibly, we have a perfect model, a correlation of 1. How did we do this? Well, you might have suspected already, this was not a fair contest. We are predicting on the training data set. So the model's already seen this data, and it's already knows what the right answer is going to be, so to speak. So this is why it's really important that we separate our training and our test sets, and we ensure that they're independent, so that the model has no prior knowledge of the data that's used in the test set. Let's look at another example down here. Instead, we will create training and test sets. Let's randomly select what will be in the training set and in the test set. And let's go ahead. We're going to, again, do a linear regression model and fit on that training set and predict on the test set this time. And we're still looking 36 months out into the future. So this is still a pretty tough task. And yet, here are our results. We have a correlation of 0.92. Incredible. This is still a pretty decent model for such a difficult problem. Why has this occurred? Well, when we randomly select the data points for our training and our test set for this particular use case, they will not be independent, the training and the test set. There is still going to be some correlation. The reason for that is that the ocean has a memory, so to speak, of about 2 years. So data that is within the same year will be correlated with that same data. It's called autocorrelation. So when we split data between training and test, we need to be sure that we are preserving that temporal nature. And that's why, if you remember earlier, when we had defined train, validation, and test, we did so by year. So let's go back up just so we can confirm. Training data was from 1980 to 1995, validation 97, 06, and test is 07 to 2017. So that is ensuring that these data sets are as independent as possible from each other. All right, I do have one exercise here, a chance for you to try this out for yourself, write some code. So we are asking you to do the same linear regression models as we did up here. So we are predicting 36 months out, but this time do it correctly and create an uncorrelated test set and then see how does the performance compare to the 2 prior examples. All right, let's talk about another main concept in machine learning that's very closely related, called the bias variance trade-off. So first, let's define these terms. Bias is defined as how well the model is predicting the ground truth. So really, how good is our model? Variance is attempting to capture as the input data is varying, how does the machine learning prediction vary in response? So if we have a very small change in those input predictors, do we see a big or a small change in the resulting ML prediction? Again, we're going to use these diagrams to illustrate these concepts. And let's start over here on the left. If you can remember, this diagram is representing an underfit model. An underfit model is going to have very high bias. So remember, bias is how well is the machine learning model predicting the truth? Not well. This is a pretty bad model. So it is high bias, but conversely, it has low variance. So if we were to perturb any of these data points, the model that results, it's probably not going to change, if at all. So low variance. So bias and variance, we call it a trade-off. If one is high, the other is low. So this diagram over here on the right, if you remember, this is our overfit model. This one is going to have low bias. So it predicts the ground truth very well, maybe too well. But conversely, it's going to have high variance. So if we were to change any of these data points here, the model itself would likely change because it is so dependent on each of these data points. So if we were to run into these situations, let's say we have an overfit model. What sort of techniques can we apply to overcome this? Well, one of them is called regularization. So this section here is going to talk a little bit about the math behind a machine learning algorithm, but we'll try to keep it high level and just talk about the intuition. So in a linear regression model, what we're trying to do is to minimize square difference between the predictions from the model, that's represented here by XW, and the ground truth, which is Y. XW, where X is the input variables and W are the weights that are discovered by the linear regression algorithm. So if we have a large W, any small change in X is going to result in a very large change in that resulting forecast. So what we want to do to regularize our model and to reduce overfitting is we're going to penalize the model when it learns large weights. We will append this regularization term here. Remember W, oops, sorry about that. W is weights. And this form in particular is called ridge regression. So let's go ahead and see this in action. We're going to create a train set on 1990 to 2005 and a test set from 2008 to 2015. Notice there are a few years here between our train and test set. If you remember earlier, we were talking about the ocean has a memory. So we're ensuring that these two train and test sets are as independent as possible. Okay, so let's go ahead and train just a linear regression model. We're not going to do anything fancy here. And here's the result. Our correlation is 0.83. Now we're going to use a ridge regression model. So let's see how this one compares. And we have a correlation of 0.88. So this is slightly better than that previous linear model. So we can see that this ridge model is generalizing a lot better on unseen data. Let's dig into this a little bit more deeply. Let's look at the variance between these two models. So what we're going to do here in this cell, we're going to perturb the test set predictors. We're just going to multiply them by a small random number. And then we're going to use the previously trained ridge regression and linear regression models to predict using this perturbed data. And then we'll record the spread in the resulting predictions. That's what this plot here is attempting to convey. Blue is going to be that linear model, and orange is the ridge model. And we can see that the orange has a smaller, a more narrow spread than the blue. So we have decreased the variance using the ridge regression model. One final check. Let's take a look at the weights that come from both the linear and the ridge regression model. Ridge here is in orange, linear in blue, and we can see the magnitude of the ridge regression weights is smaller than the linear regression weights. So great success with our regularization, and definitely a technique we'll keep in our back pocket should we come across an overfit model. All right, so we talked a lot about linear regression. Let's move into some deep learning. Let's try to train a neural network to forecast ENSO. First, we'll define some code to do so. And this is the same load ENSO indices as before, so nothing interesting there. But let's talk a little bit more about assemble predictors and predictams. So similar function to what we used previously with linear regression, but there are some changes that I'll talk through. So start date and end date are the same. Lead time is the same. The data set is just defining which data set you want to pull from. But let's talk about this data format input here. So the options that you can define are either spatial or flatten. Spatial is going to preserve those lat long dimensions. So remember, we had a 3D array previously, and when we're using a linear regression model, what we were doing was flattening it. But for a neural network, we are going to use the spatial option. We're going to preserve that 3D array because our convolutional neural network that you'll see below is capable of taking in that kind of dimensional data. We're also going to define another variable here called num input time steps. This is the number of time steps we want to use within each predictor sample. This is number of months. So if we define this as 3 months, we'll be looking within the past 3 months for those latitude, longitude temperatures. There is another discussion of that here, just so that it's very clear when we're defining this variable, what the resulting data will look like. Okay, let's define now our CNN, stands for convolutional neural network. So this is going to be a relatively simple CNN. We've got one convolutional layer here, a pooling layer, and then another convolutional layer, followed by 3 fully connected layers here. That's what these linear layers are. And then our output dimension is just 1, because we were just trying to forecast one value, which is that Nino 3.4 index. Okay, so this function is going to train our network. Let's step through this at a high level. Initially, we need to initialize our best loss. We're going to set it to infinity. So any loss is going to be better than infinity. And as we find better and better losses, we're just going to update this best loss variable here. And we're going to keep track of our train and our test losses. We're going to iterate through the number of epochs that we define. The default here is 40. So within each epoch, we are going to gather our data from either the training data or the test data. And we're going to train in this case. Our running loss will set initially to 0. Then we're going to iterate through mini batches. So that's what we're doing here. We're getting some mini batches of data, and we're going to zero out the parameter gradients. Then we will find the predictions using the mini batch predictors within the current neural network. And then we'll find the loss between those predictions and the predictants of this current mini batch. We're going to run the backward pass, so we're going to calculate the gradients of each weight with respect to the loss. And then the optimizer is going to update the weights of our neural network using those gradients and using whatever optimization algorithm that we specify. We're going to add this loss to our running loss. We're going to iterate through all of our data. And if our loss is less than our best loss, then we're going to say, okay, this is the best model that we've got. We're going to update our best loss, and then we're going to save off that model here. And again, we're going to iterate through all of our epochs and continue to run that same logic. Now down here is, well, we'll start with 79. So we're going to load whatever that best model was from training. And then we're going to just create our predictions. So here we're just running through each mini batch within the test data and creating predictions. And that's what will be eventually returned from this function along with our training losses and our test losses. All right, so let's actually run this code. We are going to define the number of input time steps. Remember, this is the number of months we want to use within our predictors as 2. And our lead time is also 2, so that's 2 months into the future that we want to be forecasting. And here, again, we are defining our dimensionality of our data as spatial. So we're going to preserve that latitude and longitude dimensions. And defining our CNN right here, our optimizer is going to be an atom optimizer with a learning rate of 0.0001. And let's train our network. We're going to use MSE as our loss. Our optimizer again is the atom optimizer, and the train loader and test loader, which we've defined here, will load in our train and test data with batch sizes of 10. So remember, we've got 40 epochs. We're going to iterate through all of those. We're going to keep track of the loss as we do so. All right, let's see how well our model performs. So in blue here, we have the training loss, which decreases pretty decently as we go through the epochs. And in orange, we have the test loss. So our test loss is spiking and doesn't seem to really be following that same curve as from the training loss. So remembering what we talked about earlier in terms of overfitting and underfitting, what is this sort of plot trying to describe? Do you think our model is overfit, or do you think it is underfit? I'm going to leave that question for you. Hopefully we've discussed this topic enough to be able to determine what might be wrong with this particular neural net. In here, we'll look at the time series against the ground truth and see how well the model is performing. All right, so I've got a few exercises here, a chance for you to experiment. In this exercise 2, I'm suggesting to reduce the number of parameters of the network. And you can do that in a variety of ways. You could either define a different network architecture or change the number of parameters within a certain layer. But it's up to you. It's a chance for you to try to see if you can tweak the model in a way to improve that performance. And then finally, the third exercise, we're going to try to use different traditional ML techniques. Previously, we were only doing linear regression. There are a lot of other algorithms we can try. In this particular exercise, I recommend using a random forest algorithm, but feel free, again, to experiment and see if you can improve the performance that we saw previously. Finally, there are several challenge exercises. These are chances for you to dive even deeper and experiment with this data and this use case. So they are all listed here, but I'm not going to go through them in great detail. Feel free, if this is a topic that interests you, to dig in and try this out for yourself. All right, and that is it. Thank you so much for sticking with me throughout this walkthrough. I hope this tutorial has shown how we can use ML techniques in a pretty traditional climate problem space. Feel free to reach out if you have any questions, and enjoy summer school.